composite functions. This fundamental technique appears throughout calculus courses and is essential for solving more complex integration problems. You'll learn to identify the inner function, find the correct differential substitution, and transform the integral into a simpler form. We'll use U-Substitution. The inner function x squared becomes u, and the x dx outside is part of du. That converts the integral into a simple cosine integral, which we evaluate and back substitute. Let's work through it on the diagram. How do you integrate x times cosine of x squared? The x squared inside the cosine makes this tricky. We can't integrate directly. Students often try integration by parts here, but notice the x out front is exactly what the chain rule would produce from x squared. That's the clue for U-substitution. Goal: evaluate the integral of x cosine x squared dx. Step 1. Identify the inner function and set u equal to it. Let u equal x squared. This is the argument inside the cosine. Differentiating, du dx equals 2x, so du equals 2x dx. Solving for x dx, we get 1/2 du. This matches the x dx piece in our integral perfectly. Now we substitute everything into the integral. Step 2. Replace every x expression with u, then integrate, replacing cosine of x squared with cosine of u, and x dx with 1/2 du. Pull the 1/2 out front. Now it's a standard cosine integral. The integral of cosine u is sine u, so we get 1/2 sine u plus c. Almost done. We just need to substitute back to the original variable. Step 3. Replace u with x squared to return to the original variable. We had 1/2 sine u plus c. Recall that u equals x squared. The final answer is 1/2 sine of x squared plus c. Quick check. Differentiate 1/2 sine x squared using the chain rule. We get x cosine x squared. It matches. Whenever you see a composite function and its inner derivative floating outside, that's the signal for U-substitution. Set u to the inner function. Express dx in terms of du, integrate the simpler form, then substitute back. The general formula: the integral of f of g of x times g prime of x dx equals the antiderivative f evaluated at g of x plus c. This is just the chain rule running in reverse.